Welcome back. Next up, we're going to hear from Tom Phelps. He's going to tell us about an interesting topic, advanced time travel with applications. Take it away.
Okay, thanks, Martin. All right, in the next half hour, we will build a time machine. More precisely, we will learn how to build a series of time machines. We'll build one, look at it, and say, that's swell, but now we have new ideas. We need another machine that's even more sophisticated. And so we'll go through that cycle a few times and come up with something that's not terrible. All right, so let me show you what I mean by a time machine. Okay, so let's say you are playing Prince of Persia. Okay, and so this is the emulator called IE, and it does support sound, but there were technical problems with the Macintosh. So, all right, so let's say you turn this way, and you say, how am I supposed to do this? Maybe I should find a sword. Oh no, so you can pause and go backwards, and now you're back, and you say, maybe I should go in the other direction. And then you can continue. And let's say you're not really familiar with how the jumping works. You fall into your death. You can go into pause, and from the spiky depths you go, oh, I just hit the spikes. This is in low res now. Switches back to high res. You fly up, and you say, maybe I should learn how to jump. And so you can also do that, and you can do this as many times as you want. Okay, so you get the idea how that works. So this is what I showed last year, and there's no special code modifications done to Prince of Persia, and this works on any software you have, so you could be running AppleWorks, and it will give you unlimited undo and redo, and that was good enough for last year. Now I call this simple time travel, and the title of the talk is Advanced Time Travel. Now, last year, I don't know if you saw the talk, but I had a lot of flashy graphics going around, and there was a lot to look at. This year is going to be different. I'm going to describe improvements to time travel. Fortunately, most of the things are abstract and technical, which is for an audience who likes slots in their computers, that's probably fine. Unfortunately, and I hate to do this to people who are on vacation or it's after lunch, but I'm going to have to sock it to you with some PowerPoint. Okay, so actually, the first one, number 0, so 0 means it's part of a series but doesn't actually count as a time machine. But they're the regular computer files that we're all familiar with and have been around forever. And they're so mundane and workhorse that we forget just how amazing they are. So they are a form of time travel because you save your word processing document or your compile or whatever, and then you can turn the power off and come back later on, and that's a form of time travel. And nowadays with the internet, you can send the files around, and so files can conquer time and space. But unfortunately, we have to rely on individual applications to translate their internal data structures to files to save out, or we rely on undo or the individual applications to do undo and redo, which are standard nowadays, but back in 1977 were not. And so what do you do if you want to run an arcade game or something that was back in the day? And so what you do is just save everything. And so we can now so the strategy of the talk is that for these first few time machines, things are kind of familiar, and we can kind of speed through that. And so we'll have more of our time to look at the more advanced time travel. So with save state, you just save everything, the RAM, the processor, all your hardware, and the weird Apple II stuff. And the only tricky thing about this for the Apple II is that you can have cards in the slots, and you can have different cards in different slots, and each card probably has its own special state that you need to save. For instance, with the disk drive, you need to save like the spin it's at. You need to save the status of the register. If it's a mouse, you need to save like the previous mouse position, so you know if you're dragging. And so it can get a little hairy to keep track of everything, but this is pretty standard in a lot of emulators. For instance, let me show you one. Well, I'll do that later. And so, but what's great then is that you can just save whatever you want, whenever you want. And so it can be an arcade game that doesn't have a save function, or it can have kind of a wacky save function. Like in Infocom games, you had 7 games that you could save at once, but you saved them to a number on a special disk, and you had to record somewhere else. Like save game 3 had this special thing that you wanted to record. An application that I haven't seen before that can be useful for Apple II programs is that it can automatically find the keyboard commands that are used in the program for you. So maybe if you were, a 12-year-old and had a game of, a disc of pirated games, maybe you had some amusement trying all the keyboard combinations to see what the commands were, and maybe nowadays it's not as fun. But what you can do in combination with the debugger is set a breakpoint or set a watch point so that whenever the keyboard is read, or the first time the keyboard is read, you save the whole machine state and then run from that point on with a null key and track instruction by instruction and see what track the value and see what the value of the key is compared to, and you can just spin out like all of the keys that are actually used, including like hidden Easter eggs, and then you remove the watch point from the keyboard and then you can play normally, and you revert back to your original state. Okay, now I'll talk about how time travel worked in IE and many other emulators. This is last year. Okay, so you build on top of save state, you save everything, and you just tell the computer to do this as often as you like. And if you do it every 10th of a second, you can get some good video playback. And this is something that should be easy for emulators to do it in this way, because you already have a timer loop going as you're running the processor, and this is just one thing that you do a little bit less often than the processor. And so this was how IE did it last year, and let me show you another. Okay, and this is a different emulator for a different system. This is a front end for a whole lot of emulator backends, and they support time travel, which I call rewind, in a general way. They just use the save state feature of the emulator, and they just capture it because that's the level of control they have. They just capture it, and they can just with one bit of code, add time travel to all the emulators that they support. And here we go. Okay. All right. One thing I think is that if you're doing time travel this way, you want it to be efficient enough that you can just always leave it on. So yesterday, Mark Lemmert was showing us the new features of Nox Archaeist, and he entered into the boss battle with a dragon that was 4 times as large as anyone in your player character set, and he saved the game before attacking the dragon. And for situations like these, where you know it's pretty dangerous, you can save your game. And in fact, it was a good thing that Mark did so, because in one round, half his party was wiped out. But ordinarily, when you're playing an arcade game or something like that, I think you want to just go in the flow of the system. You don't want to have to like manually think, oh, I need to save now. Oh, it's been 2 seconds since I last saved. I have to save again. Oh, no, you just want the system just kind of always be on. And so when it comes to time, when you're in the flow, and then you go, oh, now I've lost my man, or I need to, or in AppleWorks or whatever, and you just find now, oh, I know something's gone wrong, I want to go backwards, then you can do so. You didn't have to plan ahead. And you can do this efficiently for some amount of time, depending on how big your memory is and how fast your processor is. And you just say, like for the last, let's say 15 minutes or hour or whatever you can support, you just kind of have a circular buffer that goes around. And so when you exhaust your hour of memory space that you're saving to, then you start writing over the start of the memory space, and you can just cycle through like this. But eventually, you'll probably want something more efficient. So Everett Dirksen was a United States Senator from Illinois who was misquoted as saying, $1 billion here, $1 billion there. Pretty soon you're talking about real money. And so it's the same for this save state method, where it's especially for the old, machines from the 80s, it is a smaller amount of memory compared to what you're running it on a modern machine. But if you do it every 10th of a second, it adds up, and it's a mess if you try to save things. So, and I demonstrated the applications. Okay, so another way you could think of doing time travel is you think, well, how did I get to this point in the first place? So, well, what you did, maybe you put a disk in the drive, you turned on the computer, you booted it up, you typed some keys, you played with the joystick, maybe you hit the non-maskable interrupt button on your cracking card, and it swapped out the ROMs. And so you can try to replicate that sequence. So in the emulator, you can save all the non-deterministic events. So all of the things that the user did as opposed to the things that you can compute. And then you start from your known point, so when the computer was turned on, and you can just recompute as fast as you can. You can save. You don't have to write to the video screen, just as fast as you can. And you fold in the non-deterministic events at precisely the correct cycle. And this is feasible because you can, especially if you're trying to emulate a 1 megahertz machine, that's just kind of a random number that just happened to be used, and you can probably do it a lot faster. So if you run most emulators, like Virtual 2 or IE, and you look at see how much CPU usage they're using, it's pretty small, pretty much. So IE uses maybe 6% of one CPU core, and my machine has 4 cores, and I found that by optimizing for speed, I could get it up to 100 megahertz. So which means that I can emulate like a minute in 0.6 of a second. And actually, it could be faster, but the Apple programmers do weird things like split instructions across memory, switch boundaries, and crazy things. So you can't do obvious optimizations. So this is almost zero cost because you capture a keyboard command, maybe that's 10 bytes or 11, so you have a cycle count plus a little bit of identification information. Unfortunately, if you have to start from the start of the computer booting, if you're like an hour into the game, that's a very long time. to come back to. All right, now advanced. Okay, so let's play a game. Let's assume that time travel could just do anything, and we didn't have to worry about the practical limits of a machine. So let's say we record everything. We want to random access to any point in our time stream. So if we have a 100-hour campaign in Ultima and we want to go to hour 30, we can just do that immediately, and we can run it on any machines. And let's just say you use different techniques for modern machines, but if it's a machine back in the day, that's no problem. And it should be free in terms of memory use and disk space. So let's see how close we can come. So this wish list seems impossible to get everything, especially you're usually trading off memory versus speed, and for things to be free, that sounds impossible. But I'm here to tell you that it's probably impossible. But we can get, let's see how close we can get. So, and let's first motivate it and see why we would want to do this. So how am I doing the time?
It's 2:33.
So
Until 3.
45? Okay.
Another half hour. Yeah.
Half an hour? Half an hour was the total, so how much do I have?
About 12 minutes.
12 minutes.
You go as long as you want. So
Yes, there's a break.
It doesn't take.
Oh, all right, okay, well, all right.
Got 3 hours to go. Sorry.
All right, so why, so that was simple time travel. That lets you kind of redo on your games for the last hour or something. So why do we need advanced time travel? Well, one thing that I thought is, on Virtual Apple and archive.org, they've got a large array of archived software, and it's nice in that they have screenshots, but the screenshots can be deceptive. You don't know what's good or not. And what you want to do is something like what old arcade machines did. So you could, walk into the arcade, not know how the machine was working, how to play the game, but you could watch for a couple of minutes, and it would go through, and the arcade game would show you cool things that it could do. It would teach you how to play the game a little bit. And on the Apple II, a few games did this, most of them did not. Load Runner is one that did it, so if you looked at Road Runner, if you just booted it up, it didn't touch anything. It showed you the cool iris. It showed you a man being chased by other guys, running around, climbing, shooting holes. It showed you how you had to shoot holes and have your chasers fall into the hole, and that the hole would close up. So just watching it taught you a lot about it and showed you if it was cool or not. And it would be cool if on Virtual Apple and archive.org, they could replace the screenshots with these attract mode features. And so technically maybe you could run a video, but the problem is content generation. If you record a video, you have to say, okay, I'm now recording the video, and then do the video, and then so that's kind of work. So it'd be nice if you could just incidentally, be playing games, and then after the fact say, oh, I played these games, and I will volunteer these videos. And if you can supply these very cheaply, then that's free content generation. Okay. Another thing that you'll see on YouTube are playthroughs. So you play through the entire game, and that's sometimes useful. But wouldn't it be cool if you could then resume that game? So say you're looking at a role-playing game, and the first part of the role-playing game, you're just rolling up your characters, you're roaming the landscape, building up your low-level characters, and collecting 2 and 3 gold pieces at a time, and you have to invest a couple of hours before things get interesting. So if you have a playthrough, then you can say, okay, I'll quickly scroll through, catch the story for that amount of time, and then resume, as if I had played that. And if it's a video, that's fine for a playthrough, but you cannot then resume the game. So 4AM records, in addition to his other work, he also records boot videos sometimes. And these are interesting, and actually, at first I didn't understand the boot videos because they were like, everyone started up with a minute of booting DOS 3.3, but in addition to showing or proving that the crack works at least a little bit, and maybe there's some protection farther on, but it works at least booting up and playing initially. That's pretty useful because you can get a little flavor of the game without having to wrangle all the disks. But the problem with videos, as opposed to like recorded events, is that you fix what the video is, and if you wanted to do some video effects later, then you can't. So I am going to go into the descriptions of how things work. Okay, so there are now a variety of methods you can use to try to approach that wish list of items that we had. The first technique takes a look at the two simple methods that we had and combines them. So the saving the entire memory was nice in that it was fast, but it used a lot of memory. And the computation used very little memory, but it was slow if we had to start from the beginning of the boot. So what you can do is reduce the number of times you save the whole memory state from a tenth of a second to maybe once per minute. And then if you want to go to some intermediate point, you can compute that very quickly. And at 100 megahertz, you can go anywhere in a minute range in a 6/10 of a second. So this is a dramatic improvement in memory and only slows things down by less than a second. Okay. Another thing you can do Okay, so another thing you can do is not save everything in every snapshot. So you can, hang on. Okay. So you can probably have a hunch that not all of memory is changing on every snapshot. And you can, over here on the right, is a memory scope. It's going through and looking at all of memory every tenth of a second and coloring the values. So a green is memory that's being read, red is memory that's being written, and blue is memory that's being executed as code. And you can see that this memory up top here is mostly red and is code, and memory down here is being read, or is code and is being read. And so you only need to save the memory that changes, so the memory that's being written. And this is a particular program, but it's typical. And you notice this down at the bottom, it was red and now it's being dark red. This is part of, down here was memory that was being read in the initial load, but is now not being rewritten, so you don't need that. So. Okay, so another technique is you compare with your previous snapshot, and if it's the same value, you just zero that out. And that doesn't do anything itself to shrink the size, but then after that, you apply general purpose compression, such as the method that's used in zip files, and that actually shrinks the number of bytes. And the general purpose compression likes a lot of bytes that there are the same value, especially zeros. Okay, another situation that comes up is when you do take time travel, you change the computation stream. So usually you can, for one state you apply a certain amount of computation, you get to the next state. But if you take time travel, you've taken something out of the past and now it's completely different. But you can save the space needed by this by recording your jump start plus the number of computation cycles you need, and it takes pretty much like a handful of bytes. And you can do the same thing with a large load. So initially you have a large load. If you're in a game like Ultima and you go from the town to the dungeon, you'll probably load in a new set of programs and a lot of memory changes. And for that situation, we just drop that on the floor. We say, well, it's somewhat arbitrary on what we choose to save state and what we choose to compute. And so we saw something that was expensive to save state, so we're just going to compute that. And so it takes maybe twice as long to recover that, but that's okay, because that's a rare case. Okay, and then we have also some Appleto specific compressions that are based on the wackiness of how high-res and double high-res works. And the interesting thing about this is that you're not exactly sure what graphics are being used. So if a high-res screen was shown recently or double high-res was shown recently, you're probably correct in assuming that's used. But a lot of weird things happen, like there will be a second high-res page that's only used to repair as a background to repair the damage done by drawings on the other screen. And so the background is never actually shown itself, but should be compressed in a high-res way. And what you can do is just speculatively compress things in a variety of ways, and whatever comes up the best, compresses the best, you just keep that. And you just keep a set of flags and recording what combination of compressions you did so that you can compress them. Okay, so let's revisit our wish list. And we did pretty well. And let me go to the bottom first because that's the punchline. So last year I was saving the entire state, so all 48K or 64K or 128K, 10 times a second. And that was fine for the past hour or two, but that builds up. And with all of the compression methods for advanced time travel, we can get down from 48K per second to 4K per minute. And to put this in different terms that are easier to appreciate, perhaps, okay, let's say we wanted to buy a Tesla Roadster. This is a base price of $200,000. If we were able to negotiate with the Tesla dealer in the same way that advanced time travel is able to negotiate, we could go into the Tesla dealer, say how much? Say 200,000 base. We could say, I will give you $4.40. And they say, okay. So, okay, and okay. Now, I don't care what people here say so much as what my mom says, because my mom is a master negotiator. So she goes with my Aunt Bobby, and when my Aunt Bobby goes out to buy antique furniture for her shop, my mother does the negotiating. And when my mother needed a wagon, she went to a garage sale and said to the person, in fact, I don't even think the wagon was for sale, but it was one of the deluxe red wagons. I'm not an expert in red wagons, but my mother said, I'll give you $1 for it. And she said, okay. So my mother likes that. So what would my mother say about advanced time travel? Would she approve of my negotiating ability? I think it's safe to say that my mother would say, I could get that Tesla for $1. All right, so do we have 1 minute? Okay, so the other Steve might say one more thing. It's one more application of advanced time travel. And if you notice, we have been using computation as a compression method, but that gives us any resolution we want, including a construction resolution. And you can use a different method to implement reverse debugging. So let me first describe what reverse debugging is. So usually in regular debugging, you encounter a crash or some anomalous situation, and then you make a guess about what the cause of that could be, and then you go and you insert watch points and break points and print commands, and then you rerun the program up to that point, and you hope you've figured out, made a good guess of what the cause was. Reverse debugging does it the other way around. So you start at the crash site, and you go backwards, and so you can immediately be looking at, you can first remove the damage that the crash did, and then you can be examining the possible causes backwards, and you can very quickly determine the cause of the problem. And this has been an idea since the 1960s, but it's difficult to do on machines that have the same memory and processor speed as you had before. So on one way this could be used is in cracking games. Some games give you will tell you that you have not defeated their copy protection by clearing memory and rebooting the disk. And what you could do is set a breakpoint on the reboot of the disk, go backwards over the loop that cleared the memory, and then go into the code that detected, or that made the checks that then led to the memory clearing, and you can more quickly determine what the problem is, and it's much easier to do than boot code tracing the forward direction. And so this is a bonus. The real technical achievement is being able to take all of these wish list points and balancing the seemingly contradictory and desires to maybe get a score of, let's say maybe it's probably impossible to do all of them, but maybe we scored like a 3.8. So, okay, thank you.
Question and answer while John starts setting his stuff up, or you get?
Yeah, fine. Questions?
Does anybody have any questions? See one from Chris Torrance?
No, Chris Torrance goes last.
Who else has a hand up?
It's kind of reading between the lines, but this is implemented in.
Okay. Yeah. So let me tell you the implementation stage. So all of the advanced techniques for time travel are implemented now. The reverse debugging is not it generates the information, but it is not presently connected to the debugger.
Coming soon.
Yes. I mean, it's like the difficult parts are done. It's the last beating things into shape.
And then specifically the AEIE.
Aye.
Thank you.
Yes. So
That's the platform.
that's right. So I think that simple time travel is easy enough that just everybody should do it. So you take snapshots, you take multiple snapshots. It's, in the Nintendo emulator that I showed you. So I don't know how Micromate implements it.
We record every byte that goes recorded into memory or not. So any change in memory,
Uh-huh.
we just save the memory location.
Okay, so that's expensive in memory.
It's expensive-ish. We can
Okay.
also record to disk, but I mean it's basically so that we can get the exact timing, so you can jump out at any point rather than at a specific interval.
Okay.
Yeah.
Right, and so these advanced techniques, I think are some of them are used by like Microsoft's reverse debugger and just reverse debuggers in general, and some of them are as original as far as I know. Okay, last question, Chris Torrance.
Yay. So, have you thought about using this for doing things like Google is doing, where playing games automatically and trying to, machine learning?
Yeah, that's a different situation altogether. Now that's artificial intelligence.
Yep.
Yeah, and you need an emulator to do that kind of thing, but this what I just talked about doesn't really help you in that direction.
Cool.
Cool, thank you, Tom.
Okay, thanks.